Welcome back to the Deep Dive. I want to start today with a frustration that I think every single person listening has felt.
Oh, I think I know where this is going.
We're in this supposed golden age of AI, right? I can ask a model to write a sonnet about a toaster, in the style of Shakespeare, and it just nails it.
Oh, absolutely. It's perfect. It's funny. It rhymes.
It understands iambic pentameter better than I do. But then, maybe 10 minutes later, I ask that same genius model to do something that feels so basic. I say, hey, go to this airline's website, find me a flight to Chicago under $300, and put it in my calendar.
And what happens?
It just falls apart. It clicks the wrong button. It gets completely confused by a pop-up. Or it just, I don't know, hallucinates that it booked the flight and I'm less stranded.
And that is the classic frustrating difference between knowing and doing.
Exactly.
We've built these incredible digital encyclopedias. They've read the entire internet, but they have surprisingly little experience actually acting in the real world. They're amazing thinkers, but they're terrible agents.
And that is exactly why today's deep dive is going to be so fascinating. We are looking at a technical report from the Metwin LongCat team about their new model, LongCat-Flash-Thinking-2601.
Right.
And folks, this is not just another chatbot wrapper. This thing is a beast. It's designed specifically to bridge that gap between internal thought and, well, external action.
Beast is definitely the right word. We're talking about a 560 billion parameter model.
560 billion, which is massive. I mean, that's getting up there with the biggest proprietary models out there.
It is, but there's a really important nuance here that makes it feasible. It's built on a mixture of experts architecture and MOE.
Okay, so break that down.
So even though it has this massive brain of 560 billion parameters, it's not firing all those neurons at once for every single task. For every word or token it generates, it's only activating about 27 billion of them.
So it's selective. It's like having a team of experts in a room, a mathematician, a poet, a coder.
Right.
But if you have the math problem, you only wake up the mathematician. You don't need the poet chiming in.
Precisely. It's all about efficiency without sacrificing that breadth of knowledge. But honestly, the parameter count isn't even the main headline here.
What is?
The real story is the agentic capability. The LongCat team didn't just train this thing to chat. They trained it to use tools, to search, to navigate databases, and, critically, to troubleshoot when things go wrong.
And looking at the benchmarks in this report, it really seems like they succeeded. It's claiming state-of-the-art performance for open-source models in agentic search and tool use.
Oh, yeah. The numbers are impressive.
And in some math tasks, which we have to get to later because the numbers are just bananas, it's actually trading blows with the top-tier closed models from the big labs.
It is effectively setting a new standard for what an open model can do when you finally take the training wheels off.
So let's get into the how. Because if it were easy to make an AI that could navigate a website, everyone would have done it by now. Why is this transition from chatbot to agent so hard?
Well, it fundamentally comes down to what we call the data gap. Think about how we train these models. We just feed them the internet.
Right. Essays, Reddit threads, GitHub code, Wikipedia, everything.
Exactly. And the internet is full of knowledge. It's full of finished products. You see the final essay, you see the working code snippet on Stack Overflow where the person says, here is the solution.
Okay.
But what is the internet surprisingly empty of?
The struggle, the messy middle part.
The struggle, exactly. The agentic trajectories. You rarely find a log of a human programmer trying a tool, getting some weird error, checking the documentation, realizing they installed the wrong version, uninstalling it, trying a different flag, and then finally succeeding.
That's a great point. The internet is a highlight reel. We only see the destination, not the whole journey.
And agentic tasks are all about the journey. They have these long horizons. You might need to take 20 steps to solve a problem. If the AI has never seen the process of troubleshooting, of failing and recovering, it just panics.
So the LongCat team saw this and realized they couldn't just scrape more data because the right kind of data just didn't exist.
They had to synthesize it. They had to manufacture experience. And they did it using this mid-training strategy that relies on 3 really clever pillars.
Right, let's break those down. First one is text-driven synthesis, which sounds like they're trying to squeeze actions out of static text.
That's not a bad way to put it, actually. They mined millions of tutorials and instructional guides, but instead of just having the model read them, they converted them into tool schemas.
So if a tutorial says, click file, then save as, they turn that into, what, a structured function call.
Exactly. They translate the human language into machine API calls. They make the implicit procedures explicit.
Okay, that makes sense.
But the second method, environment-grounded synthesis, this is where I think the real genius is. This is the reverse engineering approach.
This is my favorite part of the report. It felt like a heist movie.
A heist movie.
Yeah, where they planned the getaway before they even commit the crime. They did the whole thing backwards.
It is a bit like that. Normally, you give an AI a problem and hope it finds the answer. Here, they started with the answer. They built these little lightweight Python environments and just randomly sampled a valid chain of tools.
So they might tell the computer, okay, generate a random sequence where you create a file, write a poem in it, check the file size, and then email it.
Right, and because they're generating the actions inside a code environment, they know for a fact that the code works. They execute it, it's valid, and then they work backward. They ask, what user prompt would have caused this exact sequence of actions?
That is just brilliant, because one of the biggest problems with AI agents is that they hallucinate. They think they fixed the bug, but they didn't. By generating the actions first, you guarantee the ground truth is totally solid.
Exactly. It eliminates the hallucination problem in the training data. And then the third pillar, planning-oriented augmentation, takes it one step further. It forces the model to think before it acts.
This is the reasoning part.
This is the reasoning. In standard training, a model just predicts the next word. But an agent needs a plan. So they synthesize data where the model has to choose between multiple options. They present it with a situation and say, here are 3 ways to solve this. Which one is best and why?
It's like teaching it strategy instead of just reflex.
That's it. But you can't teach strategy without a playing field. You can't just read a book about soccer. You have to get on the grass.
Which leads us to the next massive part of this report. Section 2, building the gym.
If you want to train an agent, you need an environment. And they didn't just build one sandbox, they built a multiverse. We're talking about over 10,000 distinct environments.
10,000.
Across more than 20 different domains.
And I'm guessing they didn't have a bunch of interns typing these up manually.
Definitely not. This was all automated using what they call a tool graph.
A tool graph.
Imagine a map of dependencies. In a file system, you have tools like create file, delete file, read file.
Okay, and logic says you can't read a file that doesn't exist yet.
Correct. But a model doesn't know that intuitively. The tool graph maps those relationships. It ensures that when they generate these thousands of tasks, the sequence of actions always makes logical sense. You can't put the roof on before the foundation.
And they use this graph to do a BFS-style expansion, breadth-first search.
Right.
Which to me just sounds exactly like leveling up in a video game.
It's a perfect analogy, actually. You
Yeah.
start on level 1, a few tools, simple dependencies. Once the model masters that, you expand the graph, you add more complex tools, deeper dependencies.
So you're progressively deepening the pool so the model doesn't drown.
And you're ensuring every single task is actually solvable before the model even tries it.
There's one word that keeps popping up in this section that I think is the most important one: verification.
It is the golden rule here. Every single task they synthesized came with an executable check. They don't just check if the model gave a polite answer, they check the state of the database.
Did the file actually get deleted? Did the spreadsheet cell actually change?
Exactly. If the state of the world didn't change correctly, the model failed. Period.
That feels like a huge shift. We're moving from, does this sound right, to, did this actually work?
And that's the only way to build trust. But there's a catch. Even with 10,000 perfect environments, simulations are clean. They're too perfect.
And the real world is messy.
The real world is chaotic. APIs, timeout, servers crash.
Users like me give terrible, ambiguous instructions. Hey, just fix the thing.
You're the edge case they have to plan for.
I am the ultimate stress test.
Yeah.
So how did they prepare LongCat for, well, for me? For the chaos of reality?
They embrace the chaos. This is section 3, robustness training. They put the model through a noise curriculum.
They intentionally broke things.
They did. They sabotaged their own model in a way. They introduced 2 types of noise. First, instruction noise. They took those perfect prompts and made them vague, ambiguous, or confusing.
Training the model to ask clarifying questions.
Yes, or make a reasonable assumption instead of just guessing. If you say fix it, the model needs to learn to ask, what is it? Right. And second, they introduced tool noise. This is the really nasty stuff. They simulated execution failures. The model calls a tool perfectly, the code is right, but the environment returns connection timed out.
Or a 404 error, or just half the data. So the model has to learn resilience. It can't just throw up its hands and say, error.
It has to retry. It has to try an alternative. It has to debug the environment itself. And the data in the report shows it works. The noise-trained models dominated on benchmarks designed to measure resilience.
And crucially, they didn't lose performance on the clean tasks either, so it's not a trade-off, it's just a tougher, smarter model.
It's a street-smart model. It knows that sometimes the world breaks, and it knows how to handle it.
Okay, I want to pivot to the infrastructure side of this, because training on 32,000 concurrent environments sounds like a logistical nightmare.
Oh, it is. Reinforcement learning is already so computationally expensive. Adding all these external Python environments could grind everything to a halt.
How do I get around that?
Well, normally the brain, the GPU doing the thinking, and the body, the CPU executing the tools, are tied together. If the body is waiting for a database query, the brain just sits there idle.
And idle GPUs are just burning money.
A lot of money. So they built a system called DORA, Dynamic Orchestration for Asynchronous Rollout.
DORA. It sounds friendly.
It's a beast of efficiency. The key is decoupling. DORA separates the generation from the execution. It lets the brain switch context instantly. If one environment is waiting, the brain just jumps to another task.
So it's like a master chef in a crazy busy kitchen. They don't just stand there watching the water boil.
No, absolutely not.
They're chopping vegetables for a completely different dish while that water heats up.
That is a perfect analogy. And DORA also allows for multi-version asynchronous training. The system is so continuous that the model is sometimes learning from data generated by a slightly older version of itself.
Wow.
It just keeps the pipeline completely full at all times.
There was another hardware hack in there that caught my eye. Pre-fill decode disaggregation
Yeah.
with CPU swapping. Now that is a mouthful.
It is, but the concept is actually pretty simple. Agentic tasks generate massive logs. We call this the KV cache. It's the model's short-term memory.
Okay.
If you try to keep a mile-long log of code execution in the GPU's high-speed memory, you just run out of space instantly.
And the whole training run crashes.
Right. So they swap that data back and forth to the main CPU memory, the RAM. It's slower, but DORA manages the timing so perfectly the GPU never even realizes it's waiting. It let them train this huge model on hardware that, frankly, shouldn't have been able to handle it.
It's just squeezing every last drop of performance out of the hardware. But sometimes efficiency isn't enough. You just need raw brain power. And this brings us to Section 5, and what might be the coolest named feature in the whole report: heavy thinking.
This is the real game changer. This is where we see the shift from scaling at training time, making the model bigger, to scaling at test time, just letting the model think longer.
I relate to this so much. If you ask me what 2 plus 2 is, I answer instantly. If you ask me to calculate my taxes, I need a quiet room and maybe 3 hours.
You and me both. LongCat implements this slow thinking with a two-stage process. Stage 1 is parallel reasoning.
This is scaling the width, right?
Yes. The model generates multiple independent thought trajectories, so you give it a hard math problem. It has, say, 5 different internal thinkers. One tries algebra, one tries geometry, one tries to brute force it with code, all at the same time.
Okay, so you get 5 potential paths. But having 5 answers isn't helpful if you don't know which one is right.
And that's stage 2, the summary. A dedicated summary LLM acts as the judge. It reviews all those parallel thoughts, critiques them, checks for consistency, and synthesizes the best parts into a final refined answer.
So it's not just voting, it's actual deep reasoning.
And the results are, well, they're wild. They tested this on the AME 25 benchmark. This is high-level math competition stuff.
Right.
So what do you think LongCat got in heavy thinking mode?
I mean, the way you're setting this up, it has to be good. 80, 90%.
A perfect 100%.
100%, no.
100.
That is insane.
And on the IMO answer bench, which is International Math Olympiad level, it hit 86.8%. This tells us something profound. The ability to solve these problems was already in the model.
It just needed the time and the structure to think it through.
Exactly. To think out loud and access its own knowledge.
That's a powerful idea. We don't always need a trillion parameter God model. We just need to give the 500 billion models space to breathe.
It does raise an economic question, though. Heavy thinking is expensive. You're paying for those 5 parallel thoughts and the summary LLM.
But for high-value tasks, right,
Yeah.
like scientific research or medical diagnosis, it's absolutely worth it. I'd happily pay a few cents extra to make sure the bridge doesn't collapse.
Exactly. It's a
Yeah.
trade-off. Fast mode for your emails, heavy mode for your cancer research.
Speaking of costs, there was one last innovation at the end of the report that addresses the cost of just reading all this text. Zigzag attention.
Ah, yes. The one more thing. We mentioned that agentic logs get huge. Standard attention in transformers, it scales quadratically.
Meaning if you double the text, the work to process it quadruples. It gets slow, fast.
Unsustainably slow. So LongCat introduced zigzag attention. They replaced half of the full attention layers with something called streaming sparse attention.
How does that work?
So imagine you're studying a textbook. You could read every single word on every page with intense focus. That's full attention. Or you could just read the first and last sentence of every paragraph to get the gist. That's sparse attention.
But if I just skim, I'm going to miss important details.
You would if you only skimmed. But zigzag alternates. Full layer, sparse layer, full layer, sparse layer. The information zigzags through the model. The global context is preserved by the full layers, but the computation drops because the sparse layers are doing a lot of the routing.
And the report says they can handle up to 1 million tokens of context with a 1.5x speedup. For an agent reading an entire code base, that is massive.
It effectively removes the penalty for having a long memory.
So let's bring this all home. We've got LongCat-Flash-Thinking-2601. It's trained on reverse-engineered data, exercised in 10,000 automated gyms, bullied with noise until it got tough.
Runs on this incredible decoupled infrastructure and can enter a heavy thinking trance to solve math Olympiad problems.
It's a comprehensive package. It proves that agentic capability isn't just about making the model bigger. It's about the curriculum.
It's all about the environment and the training.
And the benchmarks back it up. 73.1% on BrowseComp, 88.2% on a 2-dial bench. It's just dominating the open source space.
And critically, they release the checkpoints. This is open source, so the community can verify these results and build on top of them. We aren't just taking a press release at face value.
That transparency is huge. So wrapping this up, it feels like we are inching closer to that dream of an AI that doesn't just chat, but actually works.
We are, but I can't stop thinking about that heavy thinking mode. It leaves us with a really provocative question for the future. For years, the AI race has been about speed, instant answers, real-time generation.
Yeah, we're obsessed with latency. We want the text to scream faster than we can even read it.
But if we can achieve perfect results, literally 100% on benchmarks, just by adding more compute time, have we reached a point where the bottleneck isn't the AI's intelligence anymore?
What is it then?
It might just be our patience. Are we willing to wait 30 seconds or a minute or even an hour for an answer that is guaranteed to be correct? Or will we always demand instant gratification, even if it's wrong? The LongCat report suggests that if we just wait a moment, the answer is worth it.
That is something to mull over the next time you're staring at a loading spinner. A huge thank you to the Meitu and LongCat team for publishing this research, and thank you all for listening to the Deep Dive. We'll catch you on the next one.